Today we continue with the next imaging modality, and today we will cover ultrasound imaging, echography. So as I said before, I'm using this slide to show you the differences in some ways or the complementarities of the imaging modalities. And as I have tried to explain last time, is there's not a single imaging modality which is like ideal, or let's say it that way, which is in such a way that we only would need that. So each of them is using a different principle. So it's looking at different measurements of some physical properties of the object or the organ or the body that we try to image. And by the fact that they have different working principles, they look at different properties of the object. And so these properties are, of course, then clearly visible in the image. And as I said before, what is important to always keep in mind that you measure a physical property and that you then try to relate this to what you want clinically, namely looking at anatomy or function or blood flow or something like that. So as I said before, so we have a couple of eggs here with different times of boiling, with also like a raw egg. When we looked at X-ray imaging, as we told before, you can't see any difference between whether the eggs are boiled or not, by the fact that X-ray imaging really looks at the concentration, the local concentration of atoms in the object. That's by the principle of X-ray. And then, of course, what we do here is with projection X-ray, you really look at a projection. So that means that internally, you also can't discriminate small details. But keep in mind that it has a very high resolution as compared to the other ones. Today, we're going to cover ultrasound imaging. And what I mentioned also last time is I can't show the 4 eggs here, because with ultrasound imaging, we can only look at the hard-boiled egg, or at least at a boiled egg, in the sense that it's impossible to go through the shell of the eggs. And we will see why, because why the ultrasound cannot penetrate them. But what you also see is that it has like a unique kind of texture in some ways, and we will explain also where that comes from. One of the things you also see is that it has actually quite a good resolution. And what we will show is that actually in the direction of the scan line, ultrasound can have the highest resolution of our imaging techniques. But overall, resolution is quite difficult to determine or to define an ultrasound. So these are the things that we will cover today. So why is it called ultrasound imaging or ultrasonic imaging? Well, because actually it's based on the use of sound waves with a frequency that is higher to the human audible range. As you might know from physiology, the range of the ear of the human, so the highest frequency that actually a young person, because it of course decreases also with age, the highest frequency that you hear is about 20 kilohertz. What we will see is that when we do imaging with ultrasound, we will go to the range of the megahertz. So that means that we will, like, for example, a very typical imaging frequency would be 2.5 megahertz, so which would be kind of an order of magnitude almost larger than what we can hear. So that's why it's called ultrasound. So and we're going to use these ultrasound waves, properties of wave propagation, and especially wave reflection, in order to do imaging, so to make a graphical representation of the object. Ultrasound, or the use of ultrasound for imaging or for obtaining information of a scene of object, is of course something which is not unique to only ultrasonic imaging itself, or medical ultrasonic imaging, let's say it that way, because it has been used, and it was actually first used by humans to do non-destructive testing, and it's still being used quite a lot. For example, when you try to look at little cracks in airplanes or boats or something like that, or even bridges, or quality assurance of materials, their ultrasound is still used also quite a lot. But of course, also many of the ideas come from nature itself. And so there are several species in nature that actually use ultrasound to do imaging. And we know the sonar of the bats, of course, which is one of the typical ones. And we also know that dolphins, for example, are also using this. One of the things that actually by studying bats, for example, you can also see that bats also use several imaging techniques. As we will see later on, there are different ways to do ultrasonic imaging. And one thing is to really try to make a tomography. Yeah? So as we said, like a cross-section, like a cut through an object in order to look at the internal thing of it. So bats are also using imaging. So really trying to make a representation of, for example, the trees and the objects or insects and what they're looking for around them. But what we'll see later on also is that we actually, with ultrasound, can not only look at tomography, so for anatomy, but we can also look at, or we can also measure velocities, for example. And we do that using some Doppler effects, for example. And actually, there are also bats, and it depends on the species, that are using this. So instead of trying to make an image of their environment, what they do is they try to make an image of the velocities of their environment. And then obviously, while they're flying, whatever set of velocity which is similar to them flying is stationary, but of course insect would have a different velocity, and this makes that they can actually look at insects in a very efficient way. And actually, depending on the density of the forest that they're trying to catch insects in, they seem to be using one or the other imaging modality. So it's quite interesting actually to study the behavior or study how animals are using this and try to translate that actually into, for example, medical imaging. Okay, so what are ultrasonic waves, or the ultrasound waves that we are using? They are actually longitudinal compression waves. That's what we mainly use. There are also some shear waves that are being used currently, but we're not going to go in detail. That's for much more advanced applications. So, but for regular imaging, we use compression wave. And that is using actually the elasticity and the inertia of the medium, and we displace the medium with a certain frequency over a certain distance. So that means that an ultrasound wave arrives, and what it actually does, it would locally compress the tissue or the object and would then relax it. And of course, this is related to a local pressure, a local displacement of points, and a certain velocity, of course, that is going on. And so what we do is this pressure that is being used, we call it the acoustic pressure. And of course, you can already imagine that acoustic pressure has to be kept in a certain limit in order to try to avoid damage. Because when you would compress tissue too much, you might actually induce damage. But what is actually really important is that you see it's like it's actually an alternating pressure. That means that you both compress it, but you of course also extend it. So, and the amount of compression extension can be in a little bit similar, but you can already imagine that if you take tissue and you try to locally extend it a lot, that you have a chance that you do damage. And that's actually what is possible with ultrasound. And that's also actually, we use ultrasound also, it's called lithotripsy, which is trying to destroy, for example, stones in the kidneys or in the gallbladders and things like that. It's all based on this fact that locally you would induce a compression and an extension, and this way you would either try to image the objects, or you can actually try to destroy on purpose or not on purpose the object. So that's why this kind of pressure, this local pressure, is also quite important to understand. Obviously, since it is going on with a certain frequency, it has a certain wavelength, it has a certain wavelength in time, it has a certain wavelength in space. And so these are the things that are important and will determine some of the properties of the ultrasound. So as we said before, you can look at it as a displacement of the particle in space, and as, of course, a displacement in time. So we see already that there's these two components, is that there's space and time, which is important, and that becomes then, of course, some wave propagations. So when we look at it as a wave, so that means that we have this local oscillation in some ways of the medium, but actually this oscillation, by the fact that you have an elastic medium, so that means that if you're displacing one point, then that one will interact with the next one, and that one will interact with the next one over time. So that means that in the end, this whole wave is actually also being propagated through the object. And so that's what we say is like the wave propagation. And the wave propagation also happens with a certain speed. So at the one hand, we have the frequency of the wave that we're using. So that's the oscillation of the wave itself. So that's the ultrasound frequency. But on the other hand, this wave will displace with a certain velocity throughout the body. And that's what we actually call the sound velocity. So that's the displacement of the whole sound wave. And the sound velocity is depending on the medium. So that is actually a fixed value for a certain medium. We cannot change this. That depends on the density of the medium. And for example, in soft tissue, and that's like an average that we actually use for imaging, the velocity is about 1500 meters per second. This is fixed, we cannot use or we cannot change. So this is something that we have to always keep in mind. And so this actually, you can already start to imagine that this speed will determine how, for example, an ultrasound pulse that we would generate at the skin, so at the surface of the body, how that would propagate inside the body. And then later on, we see that actually reflections have to come back in order to do the imaging. So this speed at which this happens will actually determine a lot of our temporal properties, the temporal resolution of our imaging. So that's important to keep in mind, that that is like a fixed value for a certain tissue with an average soft tissue around 1500 meters. Okay, so how do we generate this? What is the equipment that we actually use in order to generate these ultrasound waves? Well, we use materials with what's called piezoelectric properties, so or with mechanoelectrical transducers, where we use an electrical field in order to stimulate a certain object, and then as a result, we actually generate an acoustic field. So these materials are piezo crystals, which you probably know from physics. What happens is if we take this object, we put a certain electrical field over it, what happens is that it will change its dimensions. And so by using an electrical field, we can actually compress or expand this material. And so that means that if we then do an oscillating electrical field on this object is starting to oscillate. And you can already imagine if this object oscillates, so that means that the surface is oscillating with the frequency that we actually used for the electrical stimulation. What now happens is that this object will then displace the connecting air if we have, or if we connect it to the tissue, will start to displace the tissue and thus start to initiate a wave. Now, reciprocally, what actually happens is if a mechanical wave is coming on this object, so if we actually take this object and we compress it or we expand it mechanically, what actually happens is that actually it will form an electrical field at its surface. So that means that we can use this in order to generate ultrasound waves. When we put an electrical field over it, it starts to vibrate and it will send out waves. But if a wave would come to this object and the object starts to vibrate, actually an electrical field is automatically generated on the surface or over the surface of this object, and we can actually measure this. And so we can use actually the same material as a transmitter and as a receiver for ultrasound waves. And that's actually really nice. That's a nice property. And that's then the basis of using this in order to generate ultrasounds and at the same time receive or measure ultrasounds. So as we said, yeah, it's a compression wave. And also what you will have is, of course, that will be transmitted perpendicular to the surface, because what we said, it's like this longitudinal compression wave. So in the direction of the surface, this is going to go. You can already imagine that it would have a kind of an enormously large surface, let's say it that way. What you then would generate is you would generate full plane waves. But of course, mostly our transducers have a certain length. So that means that you will see that you actually would generate more like this shape of waves. But we'll come back to that later on. Now, in reality, of course, it is based on a piezoelectric crystal, but of course, we're not putting this crystal in itself on the skin of the patient. But what we do is we create a full transducer that we then use and put on the patient. And the purpose of this transducer is to send out the ultrasound waves, and at the same time also receive these ultrasound waves, but of course only in the direction that we want to do the imaging. So that means that in reality, a transducer would roughly look like this. So we have the piezoelectric material. Of course, we need to be able to put an electrical field and measure the electrical field. So we need electrodes on the surface. So there's some kind of metal layer mostly, which would be connected to the surface with, of course, wiring that goes outside, because we need to be able to put an electrical field on top of it and measure the electrical field. So we need to connect it to electronics. What we then also want is that because crystal would vibrate at both sides, that means that you would send both to one direction and the other direction. You would send the same amount of ultrasound, but we want it only in one direction. So that means that we put a backing material, which would absorb all the waves that would go in the wrong direction, so that there's no ultrasound, of course, in the end being transmitted there. And then one of the things that you will see is that what is also important is that in order to get proper transfer or efficient transfer of the energy towards the body that we want to image, what we need is we need a matching layer. And we will see this matching layer actually has to match the acoustic properties of the piezo crystal with the object that we are imaging. And that is actually based on the acoustical impedances, which we will explain in a minute. Now, depending on the thickness of this crystal, it will actually have a natural frequency in order to vibrate, which is higher depending on the thickness. And also, like, one thing that we could do is, of course, put like a perfect sinus wave on this crystal, and we get a sinusoidal motion of this. But what very often is done is you just put like a quick electrical pulse, and then the crystal starts to vibrate, and the natural frequency it starts to vibrate depends on this thickness. And actually, it's related to the wavelength or to half of the wavelength. So that means also, and one of the things that you also know is, like, because this works on the basis of resonance, and so you might remember also again from physics, when we look at resonance phenomena means that a certain material, when we look at it in this way, would naturally resonate in this certain frequency. But what you will see is that it would actually have a certain bandwidth. That means that the biggest amplitude is at this resonance frequency, but slightly higher frequencies and slightly lower frequencies are actually also being emitted. And the further away we go from this resonance frequency, both higher frequencies and lower frequencies, the less efficient it will be. And so that means that we have a certain bandwidth. For example, might be like a Gaussian bandwidth or something like that. But that is important to keep in mind, because that means that if we will want to image at different frequencies, and we will see that depending on the application, we would want to use a higher or lower frequency, we actually will have to use different transducers. And so that means that in general, an ultrasound scanner will have, depending on where we use it, whether we use it in radiology for abdominal scanning, in cardiology for cardiac scanning, in dermatology to look at the skin or things like that, we will see that we will have actually different types of transducers with different properties. And the important property is the frequency and the bandwidth of these crystals. Okay, so when we look at the propagation of ultrasound waves in a medium, and that's what we're going to base this imaging properties on, what we have to, or what we can define is we can define the acoustic impedance of a medium. And the things that are important, and that's already what I said before, because of the principle, what is important is the acoustic pressure that we can generate and the related particle velocity. And these are related to the mass density of the object, because of course the higher the density, the more particles in some ways we have, and the different this particle velocity will be, and is also related to the acoustic wave velocity, which is related again to the medium. And so a medium has a fixed acoustic impedance, which can be defined like this. If we look at this in detail, so what happens is that, of course, different materials will have then these different properties and related different speeds of sound. So when we look, for example, at air, when we see at air, the speed of sound is relatively low. And that's actually also the speed of sound that we hear. So you see, for example, when we look at lightning, you see that when lightning is far away, when a thunderstorm is far away, you first see the light and you much later hear the thunder, because of the fact that the propagation of sound through air is actually relatively slow. And the more dense the material, actually, the faster the velocity is going to be. The more particles you have, the faster they can actually propagate the ultrasound wave. And so we see that, as I said before, soft tissues is around 1500 meters per second. And actually, most of our organs are considered soft tissue. And that's actually very closely related to water. So also for what I told you with X-ray imaging and so on, it's like most of our body has properties which is actually very closely to water. Except what is different, obviously, is bone, because bone, and especially with calcium, a lot of calcium in there, has a much higher density than the other organs, and that's what you see also. So the wave propagation speed or the sound propagation speed is much higher in bone, and would even be higher in metals. But of course, normally you don't have a lot of metal in your body. But you do have air, for example, in the lungs, and that's important. If you do imaging of the thorax, for example, you will see that, of course, this speed of sound in air is also quite important. So you will see that we have this kind of three types of materials in our body with regard to acoustic properties. At the one hand, we have air. At the other hand, we have soft tissues. And then as a third component, we have bone. And they have very different properties. And so you will see that because they have so much very different properties, the interaction of these different materials is actually quite important when we want to look at ultrasonic imaging. Okay, so in order to understand how ultrasound is propagating, well, theoretically, what we need to do is solve the wave equation. And so what we see there is that there is a local pressure, which is related to the particle displacement, and there is a time component. So we have a kind of position component, and we have a time component. We're not going to go in detail of the wave equation. That's for a course of differential equation of physics, so we're not going to cover that. But the most important that you have to remember is that there are different solutions for this equation, and that they are related to both time and space. And that is the most important component. Now, when we look at this propagation of sound waves through the tissue, so the idea is that we generate an ultrasonic wave. In general, with a transducer, we put this transducer on the skin. That's the most common way of imaging. There are different ways, but we'll come back to that later on. So you generate it on the skin, and what you then want is that these ultrasound waves are propagating to the tissue that I want to investigate. And what we will see is later on, you base your imaging on the reflection of these ultrasound, so that ultrasound has to then travel back through the transducer in order to look at this. The first thing that happens with this ultrasound wave is that actually, because of the fact that you go there, and as we said before, it's based on this displacement of particles, and we know that tissue is viscous, so we have viscous losses. So we have like heat generation actually locally because of this motion of the particles. So that means that we have energy loss while kind of propagating through the tissue. This energy loss will, of course, be more the deeper I go, but what you actually also see is that this energy loss is also related to the frequency of the propagation of the sound wave that we're using. So in general, it's an exponential decay. Yeah? So we have that the energy that we're losing is exponentially decaying, so actually very, very fastly, with what we call an attenuation coefficient. And as I said before, the higher the frequency, so the faster the particles actually have to move, what you will see is that the more the attenuation will be. So that means that we have a frequency-dependent exponential attenuation, where the higher the frequency we use, the more attenuation there will be. And also, of course, the deeper we will go, or the further we will travel, the more attenuation we will have. And what you will see is that this attenuation, again, depends on the tissue. And so we see different types of attenuation. So for example, lungs and air has much higher attenuation than water. And now we see actually that tissues can have a different attenuation than water. So as I said before, for most properties, soft tissues are very similar to water, but not for attenuation. And that is quite important. So water itself is almost not attenuating, while tissues are attenuating quite a lot, and bone is even attenuating more. And in this case, it's actually air in the lungs, which is attenuating the most. Now, when we remember that, so this attenuation is depending on the depth and is depending on the frequency. And as I said before, what you do is actually when you generate a sound wave with a transducer, you're actually generating a frequency spectrum. So this red one is what the transducer is generating. So it has a central frequency, so that depends on the thickness of the crystal that we're using in the transducer, and it generates higher ultrasound, higher frequencies, and it generates lower frequencies. But if we look at the spectrum of a sound wave that has been propagating through tissue, and now we're even talking about homogeneous tissue, so we're not even talking about reflections. But what you will see is that obviously there is attenuation, so obviously the amplitude will decrease in an exponential way. But what you will see also, as I said before, is that the higher amplitudes are actually attenuating more than the lower amplitudes. So what actually happens is that when we look at the spectrum at a certain depth, what we see is it's less, but also the peak frequency is actually being shifted towards lower frequencies because of the fact that these higher frequencies are attenuated more. So what we will see is that, there is a change in the spectrum of the ultrasound wave depending on the depth or depending on the distance that it has traveled. Keep in mind that this is a linear effect. So what happens is that each amplitude or each frequency has its own attenuation. And just as a result, the whole thing is actually changing in frequency content. But at this moment, frequencies are just linearly changed by this attenuation. Now, besides this linear attenuation, there actually is also a non-linear propagation of ultrasound. And that's also quite an important effect, which we actually can use for imaging and which is important to understand. And the easiest way to understand this is just look at the sea. So when you look at waves, so we know that waves start to break at some point. So what we see is that instead of, while deep in the sea, we will have actually a nicely sinusoidal wave. When the wave is propagating and coming to the beach, what we actually see is that this wave is starting to buckle. And the reason for this is that actually high amplitudes of the wave, so the highest points of the waves, they're actually propagating with a higher speed than the low amplitudes. So that means that the bigger the amplitude of the wave, the faster it will go. And at some point, the wave top goes faster than the bottom, and then it starts to fall over and it starts to buckle. So the same thing is happening with ultrasound waves or with acoustic waves, actually. Of course, an acoustic wave in an object cannot kind of roll over. But what happens now is that you will see is if you start with this kind of wave, what happens is that, so the thing is the wave is propagating in this direction. So what happens is that the top goes a little bit faster than the bottom. And so you go from a sinus wave, you start to become actually a triangular wave at some point. So because of the fact that the top goes faster than the lower part. And then, of course, once it's triangular, because in tissue, in object, it cannot kind of roll over like it could at the sea. So what happens is that, of course, this will go faster and faster. And in the end, what happens is it stays obviously triangular, but it actually loses its amplitude totally. So the natural propagation is that a sinusoidal wave will become more and more triangular the deeper you go, and then will actually, because of this nonlinear propagation, will actually also diminish its amplitude, independent of the attenuation. So the attenuation that that I just explained to you before is because of viscous energy loss. It's because of heat generation where you lose energy. Here, you get also an amplitude change because of the nonlinear propagation, which at the same time would also change the shape of the waveform that we put in. Now, if you remember Fourier theory, then you know a sine wave is one frequency in the Fourier domain, and a triangular wave actually has many, many more frequencies. So what happens here is that we start with one frequency and we generate new frequencies while propagating. And that's obviously non-linear, because if it would be linear and we start with one frequency, we would always keep one frequency. So when we start with one frequency and we look at the attenuation itself, then it stays that frequency. It just becomes that frequency, but smaller in amplitude. While with the nonlinear propagation, what happens is that we start generating higher and some lower frequencies. So this really is nonlinear. And mostly we generate like double frequencies and then keep on keep on generating what we call harmonic frequencies. So here, this is shown in a little bit of a realistic sound wave. So in reality, what we do is we take the transducer and we say, for example, we put like a electrical pulse on this transducer. So the transducer starts to immediately move. Its main frequency is, of course, this sinusoid, which would be the resonance frequency. But of course, it has more frequencies. And so that means that it actually has this kind of sync function-like shape in reality. So we have a certain pulse. So this is our ultrasound pulse. And what we will see is that the deeper the ultrasound pulse goes into tissue, and this is actually propagation in water that is shown here. So we see that this original shape changing becomes more triangular, becomes less. It becomes less for two reasons: that we have this harmonic conversion, so because of this nonlinear propagation, and of course also because of attenuation. In water, attenuation is not so important, and we will see that actually the nonlinear propagation is the most important in water. When we look at this in the frequency domain, so this would be the amplitude as a function of time, so that would be in the spatial domain. Here we look in the frequency domain. So what we will see is that our pulse has a main frequency with a certain bandwidth. It has some harmonics, but they are very, very low. So you see like the lowest would be like minus 40 dB, which is actually quite a lot lower. You look at the logarithmic scale. But the deeper we travel, what you will see is that now these harmonics are actually increasing in amplitude. So there's energy actually being transferred from this main frequency towards the harmonics. And so the deeper we travel, the more high frequencies we are actually having there. So then we can use this, of course. Here you see like another. So this is in this case really a measured one, where you can see that now the larger the amplitudes you get, the more you will go into this higher frequency. So that is what I'm saying. Now, this nonlinearity, which we can express in a certain parameter, we're not going to go into the mathematics of it, but this nonlinearity will depend again on the medium. And one of the things that we will see is that actually this nonlinearity, what we will see actually for water is also quite high. So that means that if we have a pulse which travels through water, it's almost not attenuating, but it's changing a lot because of this nonlinearity. Okay. So we know that an ultrasound wave that we kind of inject into a medium in some ways, or that we can put in contact with a medium, it will propagate in that medium. It will propagate, and while propagating, it will decrease its amplitude because of attenuation, like exponential attenuation, because of the viscous heat generation, and it will change its frequency content because of the nonlinearity of the propagation. So these are already two effects that happen when we travel to a medium. These two effects happen when we travel to a homogeneous medium. So what is now happening when we go into an inhomogeneous medium? So what we now have to see is like, okay, how is a wave being propagated further, and how is it changing when we encounter inhomogeneities in acoustic properties of this medium? Yeah, because when we look at a tissue, when we look at an organ by itself is very inhomogeneous. So in our body, so well, even if we start from the skin, you first have skin, then you often have a fat layer, then you have a muscle layer, and within muscles, you have, of course, your muscle cells, which are embedded in a fibrous matrix. All of these have different acoustic properties, and so tissue is very inhomogeneous. So we need to understand what happens there. So in order to understand what happens with waves in around inhomogeneities, we have to start from the basic thing is like, how can we kind of visualize, or how can we think about waves being propagating in the medium? And a simple way to look at this, and a simple way to understand this, and to actually then derive also equations if we want to, is actually talking about or looking at the Huygens principle, which is from physics. And this principle says that if we have a wave which starts here, and we want to know where at the next time point what this wave would look like, what we can do is we can look at every point which goes further, and then actually consider every point again as a point source. And so we start from a point source. The wave propagates. If we, at a later time point, want to know what this wave looks like, what we need to do is we need to go to all the points where this wave has arrived, and we can then calculate the next step by saying that every kind of point, every particle where the wave arrived is now a secondary source of, again, a spherical wave. So this way, you can already imagine that if we have a point that is vibrating, that will, of course, send its wave around in a spherical way. That means that then we come, for example, a little bit later, we have this kind of wavefront as at that moment, the propagation of where the wave propagated. If we now want to calculate the next one, what we do is every point here, we consider it again as a spherical emitter. It emits a spherical wave, and the resulting wavefront is actually the sum of all the individual spherical waves of the particles where the wave came the previous time. And so now we have a way to look at wave propagation from one step to the other, like independent of the past. And so we can every time look at, okay, what happened the previous time? And based on where the wave is, we can now calculate where the next one will be. And so we can understand how stepwise this wave is propagated. And of course, every time what we can do is take into account what is the attenuation to the next step, and what would be the change in the nonlinearity because of the nonlinear propagation, of course. So what would be then the frequency content because of that? So when we now look at this in general, so at the propagation of these waves, and they encounter inhomogeneities, what we can see now is that there's actually two major types of inhomogeneities that we encounter, and that we can actually look at differently in some ways. Of course, in the microscopic, in the mathematical sense, they're very similar to each other, but conceptually they're very different, and especially to understand it, and to understand how ultrasound is propagating through tissues, and how it's also propagating when we have different types of tissues next to each other, we kind of simplify it by saying that we have two types of interactions. And one is that if we have a change in medium, which is much, much, much larger than our wavelength, so we go from one organ to the other one, like really big organs, what we will have is we have specular or mirror reflections. And this is what happens traditionally at the mirror also. Right? So you know from physics what's happening with light at the mirror. It's exactly the same with acoustic waves. So electromagnetic and acoustic waves behave the same when we talk about waves. So that means that if we have two media, so medium 1, medium 2, with different acoustic properties, if we have an incident wave, so a certain wave with a certain amplitude is kind of coming into this medium at a certain angle, what happens is that two waves are being generated. One is a reflected wave, and one is a propagating and refracted wave, as we say. And what we will see is that the reflection is at the angle, at the opposite angle. Right? So a reflection is at the same angle as the incident angle with regard to the perpendicular of the medium. Right? So we have at the one hand a mirror reflection, and at the other hand we have a propagating wave where the angle is changing, and the angle is actually changing depending on the speed of sound difference between the two media. And what we can actually do is we can actually calculate both the amplitude change, or both of the amplitude, as well as the incident and the propagating angles, and we can express it as a function of the acoustic coefficients of the waves. So now, depending on the acoustic properties, we see that either more or less is being reflected. Right? And one of the things is that we see is that if the acoustic properties are very, very different of the two media, then we see that a lot of waves are being reflected. And so, for example, if we go from tissue to bone, and as we said before, tissue is more or less like soft tissue is more or less like water. It has a certain acoustic coefficient. Bone has a very different acoustic coefficient. So if an ultrasound wave comes from tissue to bone, it's actually almost fully reflected. There's almost no propagation of the ultrasound wave through the bone because of the fact that the properties of these two are so different. While if we go, for example, from the liver to the heart, or from the liver to some other tissue, what we will see is that there's very little reflection. And most of the acoustic waves are actually being propagated because of the fact that the acoustic properties are very similar. And so now we can already understand why what I said before is why can ultrasound not penetrate through the shell of the egg, is that, of course, if we take an ultrasound transducer, we put it on the shell of the egg. What we first have is we have the ultrasound transducer. Then we go from the transducer to air. Even if there's a very, very small air layer between the transducer and the egg, we go from the transducer to air, and then from air to kind of calcium of the shell, and then from the calcium we would go again to the soft tissue of the egg. And so because of the fact that these properties, these acoustic properties are so different, we have no transmission. Everything is just being reflected and we can't see anything. And so that's what I actually said. So we see these large reflections when we go from tissue to air, from tissue to bone, or from air to bone. And so, of course, these are tissue to air is in the lungs, but also, as I said before, from the transducer, if we put the transducer on the skin, if we just put it on the skin, there's always a very kind of microscopic layer of air. And so just putting the transducer on the skin, we will not see anything. The only way to be able to see something is that we actually put ultrasound gel on it. So what we do is we take the transducer, we put a gel, which is a liquid, or it's like, well, it's a gel with properties very similar to tissue. So we put gel, and that gel is then coming onto the skin so that there's actually no air anymore in between. And then the ultrasound is being transmitted into the body. If we then put it on, for example, on ribs, the transducer, then we will see that because of the ribs, even if there's like a small layer, of course, of skin and fat and a little bit of muscle between the transducer and the ribs would reflect everything and nothing would propagate through. So we can't do imaging when we encounter this. Similarly, if we just want to look at lungs in itself, normal lungs, unless there's water inside the lungs, but if there's air in the lungs, we will not see anything with ultrasound because ultrasound cannot pass through because everything is reflected at the boundary. So this is already one important thing, which is very important to understand ultrasonic imaging, is that we have these huge reflections, when we have a change, when we have a major change in acoustic properties, and we have three types of kind of tissue or material in our body, which is the gaseous part, the liquid part, or the tissue, soft tissue part, and then of course the solid, which is the bone part. And so we have to know what happens at these interfaces. So here you see an example of what an image or what a signal, if we would measure it, would look like. So what we have here is we have a setup. This is actually a measurement in a bowl of water. So what we have is we have the transducer that is sending out the ultrasound in water. Then we have a kind of gel-like material here in between. So it's like an elastic kind of, it's actually a gelatin, a block of gelatin that we had here. And then we have water again. So if we image this, what happens when we look at the reflections? So as long as there's propagation within the water, we just have no reflection, just a little bit of noise. When we encounter the boundary of water and the gelatin block, we see a huge reflection because we go from water to something which is a little bit more solid. So we see a big reflection. Then within the tissue, so a lot of ultrasound is being reflected, some is being propagated. When it's propagated and it's propagating within the tissue, we don't see anything anymore because it's homogeneous. There is no reflection. And then when we come again at the outside boundary of this gelatin block, so when we go from gelatin to water, we again have a large reflection. And so you will see that this way you can actually image this object, or you can image the boundaries of homogeneous objects if these objects have different acoustic properties. And so this is based on, as we said before, the mirror reflections, or in ultrasound, we call it the specular reflections. And these are actually high amplitude reflections. Now, one of the things that is also important is that you have to see that we work with a pulse with a certain length. And actually, when we have this reflection, what actually happens is that the whole pulse has to reflect. And what we actually have is that we can have interactions of these pulses. And so this is what would happen at, for example, the reflection. If an ultrasound, propagating ultrasound wave would come into bone, what we will see now is that this would be, so here we can look at it here. So this is the typical waveform, as I said before, of a realistic ultrasound pulse. What happens now is, of course, at the moment that the first part arrives, the first part is being reflected already, but at the same time, so you have a reflection and still an end wave. Of course, the effective wave is the sum of these two. So that's what I said before. It's always, you have to see, is in order to calculate what is the waveform at one point, it is the sum of all the waves that arrive there at a certain point. And what we also see is that the reflected wave in this case actually flips. So you see that, no, actually it stays the same. So it just kind of is being mirrored. So that means that at some point, at the moment that the biggest wave comes in, what actually happens is that we have an increase in this peak positive pressure because the two sum up, the two highest. Always keep in mind that acoustic waves are very often not fully symmetrical. So you have a higher pressure and a lower pressure. So what happens here is that now at this boundary, what you get is that you get a very increased, almost a double peak positive pressure at some point because of this incident and reflected wave which start to interact. Now you can already start thinking that this can become important for when we are talking about safety. So as I said before, this peak positive pressure, but later on we come back to peak negative pressure is also quite important. That determines what the local pressure will be at this point. And the higher this is, of course, the more potential for damage you have. And what happens is at an interface of where we go from a tissue, which is water-like, to a solid, what we see is we get increased positive pressures. So this is, for example, important when we do imaging of a fetus in the uterus of a woman, and we image the head of the fetus, where we have an interface of tissue and bone. You have to keep in mind that actually you can generate very, very high pressures around the skull of the fetus with potentially some safety problems. So that's important to keep in mind. So we have to look at how waves are reflected, but at the same time, we have to keep in mind what a realistic wave is looking like. And so a wave has a certain length, has a certain frequency component, and these are all important when we look at the properties of what's going on with that wave. Okay, so next, besides this kind of mirror reflections, which happen when we have two objects of different acoustic properties, where the objects are much, much larger than the wavelength. But when the object is very, very small and comes into the range of size of the wavelength of the wave we, then actually something else is happening. And you can already imagine when we look into the body, as we said before, at the one hand, you have organs, and organs, of course, are much larger than the wavelength. So at the boundaries of organs, we very often get this kind of specular reflections. But when we look within the organs, organs itself, they are not homogeneous tissue. They have, as we said before, they have cells, and cells have components. So we have mitochondria in cells or other components. And these cells and components are much more in the order of magnitude and sometimes even much smaller than the wavelength. So it's important to understand, in order to understand imaging, what happens at boundaries of objects which are much smaller than the wavelength. And so here's an example. So we have an ultrasound wave which is traveling inside the tissue. And here we have an inhomogeneity, so a very small object of different acoustic properties than the surrounding tissue. What now is happening is that at the moment that the wave passes, and as I said before, as when we go back to this Huygens principle that says that we can look at every point that a wave passes through as a secondary transmitter of spherical waves. So if this point is very, very small, what happens is that at the moment that a wave passes, this one starts to vibrate at the frequency, of course, of the wave that comes in, and is actually now transmitting a spherical wave in all directions. So that means that part of the energy is being transmitted back, but an equal part is transmitted in all directions and is even being propagated further again towards where the wave goes, travels further on. So this is what we call a scatter reflection. So a small object is actually scattering the ultrasound, and that means that it will start to act as a spherical transmitter, but will transmit energy, of course, also to the transducer. Keep in mind that if we were thinking about the specular reflection, and let me quickly go back here, what happens here is what we said before, is that the angle of the reflection is the same as the angle of incidence. That means that we can only see the component of the wave, which is, of course, if my transducer is here, if we would have a perfectly perpendicular incidence of the wave, it would perfectly perpendicular reflect back, and everything comes back to our transducer. Of course, if my transducer is here and we have an incidence like this, the wave is reflected to another side and might never arrive again at the transducer. So that is important to keep in mind, since I said before that we will try to use our transducer both as a transmitter and as a receiver. we have to keep in mind these angles. With specular reflections, we only have a lot of energy coming back if we encounter a perpendicular surface to the wave. With scatter reflections, that doesn't matter because of the fact that there will always be part of the scattering which will be exactly in the direction as where the wave came from. But you can already imagine that this is at very low energy, yeah? So the amplitude of this reflection will be much, much, much less than the reflection from the specular reflections. So then, of course, as we said before, you keep on getting this propagation, and so you have that this is a spherical transmitter. Now, what happens if we have more objects? So we have several inhomogeneities. Of course, each of these will act as a secondary reflector, and each of these, at the moment that the wave enters there, will actually start to emit energy back. Yeah? And if these objects now are further away from each other than the pulse length, what we will see is we see them as individual reflections. However, if they are very close together, what happens now is that, of course, the reflection of one of these scatterers is still going on when the next one is already starting. And as we said before, in order to look at the resulting waveform, you just have to add them. And so you see this very typical, what we call an interference pattern, where we get a lot of reflections coming back with a little bit of a shift, and they interact to each other. So in this reflection, of course, you don't recognize the original pulse anymore, and that's important. Now, you can already imagine that now, depending on the exact distance between them, so if they are shifted by half a wavelength, for example, and so they shifted in such a way that the top part here is coinciding with the, so the top positive is coinciding with the top negative part of another wave, what can happen is that they actually cancel out each other. Yeah, because they have the same frequency. If they just shift it in such a way that the positive and the negatives add up, of course, we can get zero. So here we get what we say is destructive interference. So we have waves which are reflected, but by the fact that even though they do reflect, by the fact that their phase shift is such that they destructively interfere, we don't see anything. But if, on the other hand, the positive amplitudes are just coinciding, of course, they add up. And what we get is we get constructive interference, and we actually reflections which can be much, much higher than the reflection of the individual scatterer. And so the typical appearance of an ultrasound image where we see this kind of noise, this kind of black and white spots the whole time, is actually because of this. So that's a very typical interference pattern that we get because of the scattering. And that's actually what you see here now. So if we now have a medium, so say that this gelatin block that we put in this pot of water has a lot of reflectors. So in this case, it had a lot of it had graphite, which are very small particles of graphite. What we will see is that at the boundaries of the object, so we have water. Here we have the block of gelatin with graphite. Here we have water again. So in water, there's no reflection. Then we have the specular reflection at the boundary of the object, where we go from the bulk properties of water to the bulk properties of gelatin. And then within the object, we have the interference pattern from all the individual kind of scatter reflections from the kind of little points that are inside. And you will see that this generates this kind of typical reflections in amplitude totally much less than the specular reflections, but throughout. And if we image this, we come back in a minute how we do this imaging. You see this very typical pattern where we see white and black kind of noise next to each other, which is related to the local distance of these scatterers and whether they would induce constructive or destructive interference.